Before we get started with example 4.2, I want to remind you about conservation of energy and then a change of units, energy units that is. When we apply conservation of energy, we typically say that the total energy of a system, if isolated, is a constant. And that really tells us that the total energy at state 1 is equal to the total energy at state 2. But in our case, our potential different is going to be different than, let's say, from mechanics. That means we have kinetic energy at 1 plus the potential energy at 1, and then the same thing for state 2. In our situation, we then write 1/2 mv1 squared, and our potential is the electric potential. And then at state 2, we have the same scenario here. So when we talk about conservation of energy, this is effectively what we're talking about. And the units are inappropriate because in mechanics, we use units of joules. But if you're dealing with atomic level stuff, that's too big of a unit. So units of energy in electrostatics must be small or smaller due to the fact that we deal at the atomic scale. So we need a different unit. So the standard unit is the electron volt, which is typically defined as EV. So to get a sense of what an electron volt is that imagine the energy of a test particle or test charge, in other words, plus E, between two parallel plates. So when I think about this incline, I imagine that I have an incline that's going to look something like this. So if I do it in the landscape picture, then we have an incline. And this incline is going to come all the way down to here. And this is our ground right here. So we know this is our low, up here is our high. And what we're going to place here is that we're going to place a little charge, a little test charge that has a value of positives. So in other words, it's a positive E. And we're going to just let this guy fall where we have a height difference of 1 volt. So the question is, how much initial energy does this charge have? And so we say that its initial potential energy must be the charge times the voltage, but in this case, our charge is E, and then we have 1 volt, which now is really 1 electron volt. And when you look at the unit transfer, it turns out that 1 electron volt is 1.60 times 10 to the negative 19 joules. So here is a very useful conversion factor. Okay, that's our reminder right there. So now I want to go and look at the next example. Example 7.2 or 4.2, excuse me. So the figure over here to the right shows the electric potential along the x-axis. A proton moves inside the potential well. We want to interpret the motion. There's some other stuff here, but let's just focus on A. So the first thing in A here is that we want to interpret the motion of the proton, and then we'll go calculate this other stuff. So for this figure, for this potential, and we want to interpret the motion. So let's go do that. So the first thing is I actually don't like that graph. I do not like this potential curve since it's not in the easiest form. So what am I going to do? I'm going to change it. That's the first thing that I want to do. So why do I have a problem with this curve? So this is the problem that I have with the curve. When you look at where the 0 is at, and you could see that it's not at the bottom of the potential curve. We can see here is that if I look at this point right here, right, you're seeing here is that this is at 3 volts, but this guy should be at 0 volts. Now, if it goes up by 3, note that the max here, which is at 9 volts, but if I subtract 3, we should make this guy go to 6 volts. So we want to change this curve to make it most useful. So here's the curve that I suggest. I put that curve all the way down at the bottom. So now this point here is 0 volts. And then that's going to be 1, that's going to be 2, that's going to be 3, this guy is 5, this one is 6, and we could just keep going. And this guy is in units of centimeters. So if I look at this guy right here, this guy right here is going to be 2 volts, and then this guy is going to be 6 volts. So now that is my potential function. And this makes me much more happier because my reference should be where the ground is at. So now that I have that, I want to go in and start to look at what are we looking at. Here is the given potential landscape. So when I'm looking at this, I'm really seeing a potential function, and this piece that I'm shading in yellow here, that means no particle can come into this region right here. None. So when I look at this yellow, that's what we call the forbidden region. No charge will ever be found. It's going to go from 0 up to 6 volts. And again, we're plotting the potential. You could see here is that one of these is at 1 centimeters here. This point is 3 centimeters. This point is 5 centimeters. And then this point here is 6 centimeters. So those are the important points. And again, right here, this is 2 volts. And I'm plotting this in units of centimeters here. But if we do calculations, it's got to be in meters. So for now, let's just reference this. So I need to know everything about this curve. So we can see that there are 5 different regions. 5 regions of motion. Well, the first one is that you could see that we have a region of 6 volts, and that has to be between, let's say, 0 and 1 centimeter. Now remember, writing in centimeters is not a good thing, as long as I remember to convert it when I have to. It's just nice to put it in centimeters here. Now, if I look at the first curve from 1 to 3 here, note that that's a linear line. So in other words, it's going to have a slope and an intercept that we'll have to calculate. So this is between 1 centimeter and 3 centimeters. Then we have a flat spot. That flat spot, that's the reason why I wanted to change it. That's between 3 centimeters and 5 centimeters. And then I have another linear line, which we'll have to go in and compute. And that's going to be between 5 centimeters and 6 centimeters. And then finally, this curve is going to be 2 volts if this is greater than 6 centimeters. So this here is the potential curve. So the first thing that we want to do is we need to go figure out that linear line and this linear line. So let's go do this. So what I'm saying is that we need to parameterize this curve. So let's parameterize the 2 linear lines. In other words, we got to calculate the slope on the intercept. So the first one that I'm going to say is that let's parameterize the potential between 1 and 3 centimeters. Now, the fact that I'm going to parameterize this, that means I have to convert my units from centimeters to meters. Let's do that. So now the first thing I need to do is I need to get the slope, M1. So when I look at my curve, what am I actually seeing? I have a curve that's going to look like this. And then I'm going to have a linear line, that's going like this. And I could see here is that this is 0 here. So if I look at the bottom one, this point right here, this is going to be 3 centimeters and 0 volts. And then this point up here is then going to be 0 centimeters, but it's going to be 6 volts. So now I can get the slope. So when I look at the slope of this guy, which I've called M1, that has to be, as we say, the rise over the run. So in this case, this is going to be 0 minus 6 volts. And this guy is going to be 3 minus 1 centimeters. And then I'm going to get a negative 3 volts per centimeter. But we got to convert to meters. So this tells me that this is 100 centimeters and 1 meter. So then this gives me a slope of 300 volts per meter, and that's my slope right there. So now let's do the same thing for the intercept. So if I'm looking at the intercept, I'm going to use the equation at a line. So use the equation of the line and pick one easy point. What point am I going to pick? I'm going to pick that I'm going to get 3 centimeters and 0 volts. That seems to be the easiest. So then I'm going to substitute that into the equation. So here's what I do. I'm going to say that V at x equal to 3 centimeters is then going to be 0. But we already saw that the slope was minus 300 volts per meter. And our x value is then going to be, what is it? It's going to be 3 divided by 100 meters plus B1. And we could see here is that if I solve for B1, I'm going to get a value of plus 9 volts. So now I know my full equation. So that means here that the equation of the line for the voltage between 1 and 3 centimeters is then going to have a slope of minus 300 x plus 9 volts. So I now have my equation parameterized. So let's go on to the next one. So now the next one here, we're just going to say that we want to parameterize that curve all over the second curve, just like we did the first one. So now we're parameterizing the voltage between 5 centimeters and 6 centimeters. Now, following the same procedure as before, I'm just going to say that one gets, right? We do the exact same thing. You're going to see here is that in this case, 5 centimeters between 5 and 6, I'm going to get a slope that's positive 100x minus 5 volts. So I now know my curves here. So I know everything about these curves. So now I'm just going to come over here, copy this, and say that now I know in great detail everything about the potential. So then I'm going to erase this, and I'm going to say that this guy has to be 100x minus 5 volts. The other one is minus 300x plus 9 volts. So now we have our curve. So now what we want to do is that we want to interpret the motions here. So I'm thinking I want to copy this and bring it with me. So here we are. So the interpretation of the possible motions. So the standard is, of course, is a positive test charge. So the way I see this here is that let's play imaginary energy games. Because this is all a thought process when you're dealing with the potential. And I don't know why we have a question mark there, but what are the possible motions? Now, to put this into perspective and using energy, what we want to do here is that we want to rewrite the potential field into electrical potential energy delta U of X. Which implies here is that we convert V of X versus X into U of E of X versus X, using that the electric potential is equal to, since we have a positive test charge, I'm going to say that this will then be Q times V of E. So if I look at my curve, the big difference here is then going to look like this. So I look at this guy. So now it's not voltage anymore. What is it? It's potential energy. And so what we have to do here is that we have to convert these guys into electron volts, which is now units of energy. So what are the possible motions? So the possible motions when a test charge placed where? Well, in the first case, you could see here is that if you put it in between 3 and 5. So if I look at 3 centimeters and between 5 centimeters, that's flat. So this is a flat surface, which then tells us here that the test charge remains stationary. There's nothing there. There's no electric field, there's nothing. So now if I go to the next piece that I want to look at, I want to look at what happens if I was to place it at x equal to 2 centimeters. So if I look at x equal to 2, you could imagine here that I'm going to put it right here, and it's going to be right on the incline. So if I put it right on the incline, it can't stay there. So at x equal to 2 centimeters, we'll find here is that it will oscillate between, wait, am I doing this right? Nope, I don't want to put that at 2 centimeters. Nope, I don't want to put that at 2 centimeters. And the reason why I don't want to put that at 2 centimeters is it's going to go right out of bounds. So what I need is I need to put this guy right here. So if I look at it, I'm going to say I want it at, looks like 2.5 centimeters. So if I'm at 2.5 centimeters, what's going to happen is it's going to oscillate between 2.5 centimeters and 6 centimeters. So how can I be certain about that? So the first thing that we want to do is that we want to look at the total energy, and we could put numbers in because we could use the chart. So if I look at this, I have a total amount of energy right here. So when I look at the total energy here, I'm going to see here is that that comes up, and this total energy brings me to 2 electron volts, which I did not change. So if I look at this point, and this is going to be the potential at 2.5 centimeters, then that value automatically gives me 2 electron volts. So if I just place it there, then I'm immediately going to say here is that right here, there is no kinetic energy at 2.5 volts. So now I have my line. And my line says this, that the total energy of the system has to be 2 electron volts. It can't go above it and it can't go below it. So then I'm going to start to move as I go along this way here. Now, if you look at this thing here, what happens if I get to, is that, it's not 2.5, it's really 2.25, about. So I gotta be careful how I'm writing these numbers here, because I'm clearly screwing up right now. So this is 2.5, and this would be 2.5. So if I start to look at these numbers here, then let's say if it gets all the way down to the bottom at 3, then that energy has to be exactly the same. So if I look at this, the potential at 3 here, well, that's 0 because we're at the bottom. So then that tells me that the rest of the energy here must be kinetic energy. So in this case, we know what that kinetic energy, it has to be 2 electron volts. So now if I go all the way to 5, that particle continues to move. And note that this guy at 5 centimeters is still 2 electron volts because there's no potential whatsoever. So when I'm looking at this and I get to 5, that is still 0. Now, let's say that I now start going uphill. And the point I want to focus on is this guy right here at 5.5. So if I look at 5.5, here's what I'm seeing. You could see that at 5.5, it goes up 1 square. So all of a sudden, I now have a potential value at 5.5 that's going to equal 1 electron volt, which then tells me that this here must be kinetic energy of 5.5 that's equal to 1 volt as well. Again, continuing to move, and let's say the highest that I can go here would be at 6 centimeters. At 6 centimeters, what you're going to find here is that all of the energy has now been converted into potential energy, and that guy has to be 2 electron volts, where this kinetic energy at 6 must be 0. So if I look at this thing, what can I conclude? So at this point, when the kinetic energy is 0, we have max electrical potential energy, and we then say this is a turning point. That means the particle has to turn around. And you could see that right here, this also means that this should be another turning point. Because if it heads to the left, it can only go up to the same height at 2.5, which is 2 electron volts. So what we're seeing here is that this particle is bound. So this is a bound state of the test charge. And it represents a bound electron in an atom. That's what we mean by a bound state. Now, the other location I'd like to look at is as the final one. Let's say that we look at the position x equal to 1 centimeters. What we'll see here is that the test charge will escape to the right. Now note that we did quite a few points here, so I'm going to be more brief with this one here. So if I come back, I want to look at this guy. So instead of going back and forth, let's just place this guy right here. So we're right here. And now what I want to do is get rid of these blue points. And now we're going to take a test charge and put it right here. So if I put it right here, well, you can see that it's higher off the ground. So if it's higher off the ground, then the potential has to be higher compared to this other case. So now what I'm looking at is that I have a higher potential energy at 1, which is 6 electron volts. And in this situation, we're going to assume that we put this at rest, so then it's a turning point, so it does that. So once again, this is my potential. That means that this is the total energy is equal to 6 electron volts. So now we can just move very quickly. If I go to 0.3, it all got transferred into kinetic energy at K3. And in this case here, I'm going to have 6 volts, 6 electron volts, while having 0 potential energy. And if I come all the way to points at 6 centimeters, you could see that if I get to 6 centimeters, look at the potential. It's up 2 volts. So if I look at here, this would be the potential at 6, but this guy is 2 electron volts. So that means here that the rest of this must be kinetic energy. And so this kinetic energy at 6 is 4 electron volts. So then what you can see here is that this guy will now continue to move to the right here with the same energy. For example, if I look at the 0.7, here's the 0.7 right here. If I look at the 0.7, well, the potential energy does not change. And neither does its speed. At 0.7, it just continues to have the same amount of kinetic energy as it did at 0.6. So that's what I mean by analyzing this motion. And what I would say here is that if I was to write anything, I would say that this escaping charge represents what we mean by an electron being ionized from an atom. Okay, so the next thing that we want to look at is that we want to go in and we want to look at what we started to look at. And one of the things that we're asked to calculate is the forces. So now, from our mechanics course, if you're here from Cabrillo, this is Physics 4A. The relationship between force and potential field is this. The force is the negative derivative of the potential energy function. But we know that the potential energy is the charge times the voltage here, or potential, excuse me. So if I write this out, this is really minus Q dVE dx, where dV dx can also be interpreted as the slope of V of x versus x. And note, we calculated those already. We needed those slopes. So the only non-zero slopes occur for V between 1 centimeter and 3 centimeters. And we found here is that this guy was a negative slope equal to minus 300 volts per meter. And the voltage between 5 centimeters and 6 centimeters, we saw that that had a positive slope equal to 100 volts per meter. So what are the forces? Or the force applied by the potential or potentials? Well, here's what we have. So if I look at the voltage between 1 and 3 centimeters, we saw that we had a curve that looked something like this. So when you're looking at that curve, we imagine that's the left side here. So we know that this was at 1 centimeter and this was at 6 volts. You know what? Yeah, I want to make that in black. And then over here, the bottom point, this was at 3 centimeters and 0 volts. And so when a charge interacts with this barrier where it can't escape, then we know it's going in that direction. So if we're going to repel it, that means that the force has to be in this direction right here. So what is that force? Well, this force is then going to equal to minus Q delta V over delta X. And this will be equal to minus E, but we already calculated the slope, which is 300 volts per meter. Or this could be 300 electron volts per meter. But if we're trying to put this into newtons, then this should be positive 1.6 times 10 to the negative 19, coulombs. And then we're going to have 300, and it's going to have units of newtons. So if I compute this number will then be 4.8 in the positive direction times 10 to the minus 7 newtons. And this will be the force going to the right. Now look at those numbers. You got to admit, those numbers are crazy. Do I have any feel for a number that's 10 to the negative 17? Of course not. Now, if I go to the next potential, this was between 5 centimeters and 6 centimeters. So when I'm looking at that guy, here's what we have. I have a positive slope here. And so I could look at both my points here. This point is 5 centimeters and 0. This point over here is 6 centimeters at 2 volts. So if I look at a charge here, by the way, I did not give you, I should have put positive and negative like this. So if I make this the negative and positive in that direction, then I'm going to have a charge moving this way. And as a consequence, I'm going to have a force going leftwards that goes like that. So since we've already done the calculation, we'll just do this fairly quickly and just say that this force going to the left is again minus delta V over delta X. Here we have a positive 100 volts per meter. And then this finally gives us a value of minus 1.6 times 10 to the negative 17 newtons. And that's going to be the force to the left. So now let's go do part B and C. Okay. So B says that a proton is released at x equal to 3.5 centimeters with an initial kinetic energy going left. What is the coordinate and potential value of its turning point? Okay, let's go get that curve. So this is the curve that we've been dealing with. And so we're saying here is that the proton, and I know I keep saying positive test charge, but it's a proton, is located at x equal to 3.5 centimeters with kinetic energy equal to 4.00 headed left. So if I look at this picture here, here's what I'm seeing. So it's saying that it's at 4, so it's going to be 1, 2, 3, 4. This right here is 4 electron volts. So that tells me here that this is my line right here. This right here is my total energy line. So the question is that how much energy is that? So for starters here, we got to go to 3.5. At 3.5, we're talking it's right here. This red line represents the kinetic energy, which is 4 electron volts. And we know we are going to the right. So if I go all the way, so when we say a turning point, so a turning point implies maximum electrical potential energy and kinetic energy equal to 0. So when I look at this point, I can see here is that this point is about right here. So if I look at that, you can see that that's past 1.5 and it looks like it's right in between. That tells me then that if it's maximum kinetic energy, then this guy has to be 4.00 electron volts, and the turning point appears to look at 1.75 centimeters. And you know what? I think I'm going to move this over a little bit. That it looks like it's pretty damn close to 1.75 centimeters. And I'm going to say that's what they're asking for right there. So now, if I go to C, it's asking for this detail. This might be too long. It is. So C says if the proton moves to the right with the same kinetic energy, what is its speed at 6 centimeters? Let's see if I still have the curve. Nope, I don't have the curve. I'm going to have to grab this one and then I'll modify it. So if I look at this curve, now they're telling us that it's going to the right here. So if it's going to the right, you could see that when I get to 6 centimeters, you could see that right here, I have this amount of potential energy, and there is left over kinetic energy right here. So in this case, this is the kinetic energy at 6. This is the potential at 6. And so from conservation of energy, we have this. We know that the total energy cannot change. So this guy has to equal 6, not 6, 4 electron volts. And that has to equal to the potential at 6 centimeters plus the kinetic energy at 6 centimeters. But we can read the potential energy, and we could see here that that's at 2. So then this tells me here that I can write this as 2 electron volts plus the kinetic energy at 6 centimeters. That immediately tells us that the kinetic energy at 6 centimeters must be 2 electron volts. No, we just use the definition of kinetic energy. The definition of kinetic energy, we could then write that the kinetic energy at 6 centimeters must be 1/2 m of the proton velocity at 6 centimeters squared. So now if I go solve for the velocity, we could see here is that this has to be, by manipulating, this will be 2 times the kinetic energy of 6 at 6 centimeters divided by the mass of the proton. And of course, there's the square root. So if I know that that 1 electron volt can now go is 1.60 times 10 to the minus 19 joules per electron volt. And we know that the mass of the proton, if you just Google that, that's going to be 1.67 times 10 to the minus 27 kilograms. So if you plug this whole thing in, you're going to find that this thing is moving at 20,000 meters per second.